Look at the night sky, and you are seeing a fraction of reality. Everything we can observe, every star, planet, and glowing cloud of gas, accounts for barely 5% of the universe. The rest is entirely missing from our direct view. Modern cosmology is built on a rather uncomfortable paradox known as the 95% deficit. The standard cosmological model, formerly called lambda CDM, strictly requires two invisible components to make the physics of our universe function: dark matter and dark energy. Dark matter acts as the invisible cosmic scaffolding. When astronomers measure the rotation speeds of galaxies, their outer edges spin far too fast to be held together by the gravity of visible mass alone. Something unseen must provide extra structural cohesion. Dark energy, conversely, drives things apart. It acts as an unknown repulsive energy field responsible for the accelerating expansion rate of the cosmos, counteracting the inward pull of gravity on a massive scale. Together, these forces form the dark sector. It is crucial to understand that dark matter and dark energy are not related substances. They are distinct phenomena with completely opposite gravitational effects on cosmic structure, yet they collectively dominate the total mass energy budget of the universe. We know this invisible sector exists because of two primary evidence anchors. First, historical observations of Type 1a supernovae in the late 1990s definitively proved that the expansion of the universe is accelerating rather than slowing down over time. Second, precision data from the Planck satellite mapping the cosmic microwave background radiation locked in the exact ratio, roughly 27% dark matter and 68% dark energy. The baryonic matter we interact with is practically a cosmic rounding error. Despite decades of targeted searching, the exact physical nature of this 95% deficit remains entirely theoretical. We only infer its existence through indirect gravitational effects on the visible 5%. We have never isolated a physical particle of dark matter. There is also a prominent alternative explanation. The missing 95% might actually be an artifact of applying incorrect gravitational laws at cosmological scales. Models involving modified gravity suggest that local galactic anomalies might be explained without relying on invisible mass. To truly test whether we are missing particles or fundamentally misunderstanding gravity, we need more than scattered deep space photographs. We require a targeted geometric mapping tool capable of surveying the precise shape of the cosmos on a massive statistical scale. Enter the European Space Agency's Euclid mission, a specialized observatory launched in July 2023. Currently stationed at the L2 Lagrange point, a gravitationally stable orbit a million miles from Earth, Euclid is not designed for traditional exploratory astronomy. Instead, it operates as a dedicated geometry engine. Euclid's primary directive is to map the structural evolution of the universe across 15,000 square degrees, capturing more than a third of the entire night sky in unprecedented optical and near-infrared detail. By executing this massive spatial survey, Euclid aims to measure the exact influence of the dark sector over the last 10 billion years. It treats the observable universe as a single, interconnected web of gravitational forces waiting to be mathematically decoded. With the dark sector clearly defined as a rigorous geometric problem, astronomers now have a tool capable of measuring the shape of space itself. But how exactly does a telescope see a cosmic geometry composed of entirely invisible mass? To map an invisible architecture, you cannot look for the structure itself. Instead, you must observe how that invisible mass mathematically distorts the visible light of the background universe on a macroscopic scale, tracking subtle gravitational ripples across the void. Traditional flagship observatories like the Hubble or James Webb Space Telescopes operate on a strictly pencil beam philosophy. They stare deeply into exceedingly narrow patches of the sky for hundreds of hours to resolve individual, ultra-distant targets with exquisite chemical precision. One might assume these deep, narrow surveys are sufficient to extrapolate universe-wide cosmological parameters. However, local cosmic variance, the natural, chaotic unevenness of matter distribution across different galactic neighborhoods, means a narrow field cannot reliably represent the global geometry of the cosmos. Euclid fundamentally breaks from this targeted high-resolution paradigm. It is explicitly designed to capture statistically massive volumes of the sky, prioritizing sheer spatial coverage over the extreme depth required to study the evolutionary history of individual, isolated galactic structures. To achieve this macroscopic map, the spacecraft utilizes a highly optimized step-and-stare observational cadence. It points at a specific celestial coordinate, captures the necessary incoming light, and rapidly pivots to the next adjacent field without lingering for excessive photon accumulation. Every single pointing of Euclid's optical payload captures an area greater than half a square degree. This represents a dedicated field of view roughly 2.5 times the size of the full moon, acquired in a single, perfectly calibrated exposure. This rapid, wide-angle cadence powers Euclid's primary mission objective, the wide survey. Over its 6-year operational lifespan at the L2 Lagrange point, the telescope will systematically tile its observations across an unprecedented 15,000 square degrees of the celestial sphere. That 15,000 square degree footprint covers more than 1/3 of the entire observable night sky. The trajectory is carefully plotted to avoid the Milky Way's galactic plane and our solar system's ecliptic plane, where local dust and gas heavily obscure extragalactic light. Across this vast, unobstructed dark canvas, the mission will catalog and measure the precise structural shapes and distances of over 1 billion individual galaxies. This creates a dataset where local anomalies are entirely drowned out by overwhelming, universe-spanning statistical consensus. This strategy inherently carries a strict observational trade-off. Wide surveys naturally suffer from lower signal-to-noise ratios for extremely faint or distant individual objects compared to targeted observatories, prioritizing the breadth of the field over the absolute density of collected photons. This defines exactly why Euclid is not meant to replace or surpass telescopes like JWST. They possess entirely complementary scientific goals. Webb investigates the complex astrophysics of specific early universe objects, while Euclid maps the macroscopic geometric fabric that actually contains them. By systematically measuring billions of galaxies distributed across 10 billion years of cosmic history, Euclid constructs a three-dimensional model of the dark matter web. It shifts the analytical focus from the precise details of the dark universe to the sheer statistical volume of its gravitational influence. This macroscopic catalog forms the mathematical backbone of the mission's impending 2026 data drop. Yet, the reliability of a billion galaxy-wide survey relies entirely on an incredibly precise, baseline understanding of the spacecraft's own optical biases, detector limitations, and background noise floors. While the primary wide survey provides the necessary statistical volume to challenge the standard model of cosmology, calibrating this massive data set requires highly specialized, concentrated calibration zones. Where does Euclid point when it needs to understand the absolute faintest edges of its own data? When Euclid needs to understand the absolute faintest edges of its own data, it does not point toward glowing nebulae or crowded galactic centers. Instead, it deliberately locks its sensors onto some of the emptiest patches of the night sky. A common misconception is that deep space telescopes are always aimed at inherently unique or visually dramatic targets. In reality, Euclid's deep fields were chosen for the exact opposite reason, an extreme lack of local foreground obstruction and stellar crowding. Mission planners designated 3 highly specific observational windows, the North, South, and Fornax deep fields. Combined, these 3 distinct celestial regions cover roughly 40 to 50 square degrees of the overarching survey map, acting as pristine viewing portals. To put that geometric scale into perspective, the primary wide survey will eventually map 15,000 square degrees of the cosmos. The deep fields represent a fractional footprint, but they serve as the vital mathematical calibration anchor for the entire massive project. By locking onto these specific coordinates for prolonged, uninterrupted exposure times, the spacecraft drastically increases its overall photon collection rate. This extended stare allows the telescope to reliably reach sensitivities 2 full magnitudes deeper than the standard wide-area scans. In astronomical terms, pushing 2 magnitudes deeper means detecting light sources that are over 6 times fainter than normal. This fundamentally boosts the signal-to-noise ratio, revealing distant morphological details that would just be background static in the main survey pipeline. This extreme depth provides a vital scientific function. To accurately measure weak gravitational lensing across a third of the entire sky, astrophysicists need an absolute, high-fidelity baseline of what the faintest, most heavily distorted background galaxies actually look like. The deep fields act as a foundational Rosetta Stone. By perfectly characterizing the subtle shapes of millions of galaxies within these 40 square degrees, researchers can confidently calibrate their computational algorithms to process the noisier data across the remaining survey. To achieve this unparalleled clarity, the deep fields are deliberately located at high ecliptic latitudes. By looking straight up and out of the Milky Way's dense stellar disk, the telescope effectively avoids the thickest bands of local cosmic dust. However, even these meticulously chosen pristine windows are not entirely flawless. The limits of this deep calibration are bound by galactic cirrus, faint, diffuse, and currently unmapped clouds of foreground Milky Way dust that can still subtly skew these baseline optical measurements. An alternative approach suggests that this exact calibration could be achieved purely through overlapping observations with next-generation, massive ground-based telescopes. However, Earth's atmospheric turbulence introduces microscopic optical distortions that are incredibly difficult to perfectly model and remove mathematically. If ground-based atmospheric distortion was fully correctable through adaptive optics, a dedicated space-based deep field might actually be scientifically redundant. But because extreme precision is required to test general relativity, Euclid must capture its own uncompromising, vacuum-based baseline. While the initial early release observations gave us a brief, captivating glimpse, the true calibration power will be unlocked in 2026. Data Release 1 will finally deliver the rigorous, statistically significant baseline measurements derived from these specific deep sky anchors. To simultaneously capture both the sweeping breadth of the primary survey and the agonizingly faint limits of the deep fields, the spacecraft requires an optical sensor of unprecedented physical scale. What kind of camera is required to capture the microscopic shadows of dark matter across 1 billion pixels? To capture the microscopic shadows of dark matter across 1 billion pixels, the European Space Agency had to construct one of the most precise digital cameras ever sent into space. This engineering marvel is Euclid's visible instrument, universally known as VIS. Operating in the freezing void of the L2 Lagrange point, VIS pushes the absolute limits of optical engineering. The detector is built around a physical 600 megapixel visible light focal plane consisting of 36 tightly packed charge-coupled devices operating in perfect synchrony. To truly grasp this immense scale, imagine printing a single full-resolution image from this instrument. The resulting photograph would be the size of a standard soccer field, yet it would remain incredibly sharp, down to the millimeter across its entire surface. However, there is a common misconception about deep space telescopes that needs to be addressed. In the context of the Euclid mission, packing more megapixels into a sensor does not simply mean taking more beautiful, colorful pictures for public outreach. Instead, for the VIS instrument, a massive pixel count strictly translates to capturing more statistically viable galaxy shapes. The ultimate cosmological goal is measuring galaxy ellipticity with a pristine point spread function across an exceptionally wide field of view. Some might argue that an infrared instrument alone, similar to Euclid's companion NISP detector, could be sufficient for these crucial shape measurements. However, the answer to why VIS is mandatory lies in the fundamental limits of optical physics and light diffraction. Infrared wavelengths are intrinsically longer, which permanently limits the maximum achievable sharpness of a telescope of Euclid-specific diameter. Only visible light photons can provide the razor-sharp boundaries necessary to calculate the minute, microscopic distortions of distant background galaxies. Maintaining this unprecedented level of extreme sharpness requires absolute thermal and mechanical stability in the vacuum of space. As the spacecraft scans the heavens, the VIS instrument captures vast swaths of the deep fields, generating massive amounts of telemetry continuously. The sheer volume of this cosmic survey is staggering for an orbital observatory. Euclid generates approximately 100 gigabytes of raw scientific data every single day, beaming this massive payload of astronomical information back to ground processing stations on Earth. But operating a million miles away, far beyond the protective magnetic shield of Earth, comes with severe environmental hazards. The L2 environment is constantly bombarded by high-energy solar protons and relentless, high-velocity galactic cosmic rays. Over the planned 6-year duration of the mission, this constant radiation damage slowly degrades the sensitive camera hardware. The high-energy strikes create microscopic traps in the silicon lattice of the CCDs, directly reducing their vital charge transfer efficiency over time. Left unchecked by scientists, this progressive hardware degradation would smear the delicate images of target galaxies, entirely ruining the precise shape measurements. To counteract this physical decay, engineers must apply constant, highly complex software corrections to the raw data. Every single captured photon must be meticulously calibrated against these evolving radiation scars. It is an arduous mathematical process, but it guarantees that the VIS instrument maintains the supreme optical fidelity required for the upcoming Data Release 1. With a camera stable enough to capture billions of pristine, mathematically precise galaxy shapes across the sky, scientists are finally equipped to map the massive, invisible structures that are secretly distorting them. The hardware is fully operational, and the deep fields are locked in focus. But how exactly does observing the subtle, stretched shape of a distant background galaxy reveal the physical presence of a massive foreground object we cannot even see? The answer lies in one of Albert Einstein's most profound predictions from General Relativity: gravity bends light. When ancient photons from a distant galaxy travel toward Earth, they must navigate a vast cosmic obstacle course filled with unseen mass. If those photons pass near a massive cosmic structure, like a massive galaxy cluster heavily embedded in a dense dark matter halo, the intense gravitational field warps the fabric of space-time itself, fundamentally altering the light's final trajectory. Popular astronomy often illustrates this concept with strong gravitational lensing, where extreme gravity produces dramatic, highly visible glowing arcs or duplicate images. But Euclid's primary cosmological mapping tool relies on a much more subtle physical phenomenon: weak gravitational lensing. Instead of creating spectacular optical illusions, weak lensing induces a microscopic, almost imperceptible shearing effect. The intervening web of dark matter acts as an irregular magnifying glass, subtly stretching the apparent ellipticity of the background light sources along specific axes. This gravity-induced cosmic shear is incredibly faint. On average, the physical shape of a background galaxy is distorted by a mere 1%. Consequently, in any single isolated observation, this gravitational stretching remains entirely invisible against the galaxy's natural morphology. Because galaxies form with naturally elliptical shapes and are oriented at entirely random angles, astronomers cannot look at just one and determine if it was stretched. The measurement demands an immense statistical sample to separate the true gravitational signal from intrinsic galaxy shapes. This absolute need for sheer volume explains why Euclid is designed to capture the precise shapes of billions of galaxies across more than a third of the sky. By statistically averaging millions of adjacent galaxies, a distinct structural pattern finally emerges. If an entire field of background galaxies appears systematically stretched in the exact same direction, it reliably indicates a massive foreground concentration of dark matter. This statistical correlation enables shear tomography, allowing cosmologists to map the 3D distribution of the invisible universe. When the 2026 Data Release 1 is published, scientists will deploy this tomographic modeling to achieve an unprecedented target accuracy of 1% precision on the universe's expansion history. It translates the billion-pixel hardware capabilities of VIS into a core cosmological measurement. However, extracting this pristine physical signal involves confronting a major astrophysical boundary known as intrinsic alignment. This phenomenon occurs when neighboring galaxies form with inherently aligned physical orientations due to localized gravitational tidal forces, creating a highly convincing false signature. If a massive cluster of galaxies physically formed spinning in the exact same orientation, this localized alignment perfectly mimics the weak lensing signal. The observed stretching could be entirely due to local tidal forces during galaxy formation, rather than an intervening dark matter halo. To validate the DR1 dark matter maps, researchers must mathematically prove that these galaxy orientations in deep space are fundamentally non-random and perfectly correlated with foreground massive structures, carefully separating true gravitational shear from local baryonic alignment dynamics. By meticulously charting these minute 1% distortions across the deep fields, weak gravitational lensing effectively traces the precise clumping of dark matter over 10 billion years of cosmic history, revealing the hidden architectural scaffolding of the entire cosmos. While weak lensing successfully maps the complex clumping of dark matter, tracking the universe's accelerated expansion over time requires a standard ruler to measure the exact physical distance between those clumps. What ancient acoustic waves act as the universe's built-in measuring stick? To understand cosmic expansion, we must look for a specific geometric pattern frozen in the distribution of galaxies, a phenomenon known as Baryon acoustic oscillations, or BAO. These are not literal sound waves propagating through space today, but rather fossilized ripples from the dawn of time. In the first 380,000 years after the Big Bang, the universe was a violently hot, dense plasma of photons and baryons. Within this blinding fog, the immense outward pressure of light battled the inward pull of gravity, creating massive pressure waves that rippled through the primordial soup. When the cosmos finally cooled enough for neutral atoms to form, the light escaped, and these acoustic waves abruptly stalled. The denser rings of matter where the waves stopped became the gravitational seeds where galaxies would eventually form billions of years later. Because we know the exact speed of sound in that primordial plasma and the age of the universe when recombination occurred, physicists can calculate the absolute physical size of these fossilized rings. Today, that preferred distance scale between galaxies is approximately 150 megaparsecs, or nearly 500 million light-years. To measure this 150 megaparsec ruler across deep time, Euclid relies on its second major instrument, the Near-Infrared Spectrometer and Photometer, or NISP. While the VIS camera maps the shape of dark matter, NISP acts as an unparalleled cosmic depth gauge. NISP captures the spectroscopic redshift of tens of millions of galaxies, dispersing their light into distinct wavelengths. This allows astronomers to calculate precisely how far away each galaxy is, transforming a flat two-dimensional image of the sky into a massive 3D map of the universe. By measuring the apparent size of the 150 megaparsec BAO ring at different distances, and therefore different epochs in cosmic history, Euclid can track the exact rate of the universe's expansion over time. It is a built-in standard ruler that scales perfectly as space stretches. However, reading this cosmic ruler is incredibly difficult due to the chaos of late-stage cosmic evolution. Over billions of years, the gravitational pull between galaxies causes nonlinear structure formation, effectively smearing the pristine BAO signal and making the 150 megaparsec peak harder to detect. To recover the original acoustic ring, cosmologists must use complex reconstruction algorithms, effectively rewinding the clock to reverse the local gravitational clustering of galaxies. This highly intensive data processing is why the sheer volume of Euclid's data release 1 is so critical for statistical accuracy. There are even alternative interpretations that must be rigorously ruled out by this massive data set. Some theorists suggest that the observed galaxy clustering scales might actually be driven by unknown dark matter decay processes rather than primordial acoustic waves, which Euclid's precision will test. The classic BAO model could face serious challenges if DR1 reveals that this standard 150 megaparsec scale varies drastically depending on the specific direction we look. Such a discovery would violate the foundational assumption that the universe is isotropic, completely upending the standard cosmological model. By combining the structural map from weak gravitational lensing with the precise expansion ruler of Baryon acoustic oscillations, Euclid deploys a dual-pronged approach. This dual measurement eliminates relying on a single experimental method, drastically reducing the margin for systemic error in mapping the dark universe. Euclid is perfectly positioned to address cosmology's most glaring contradiction by providing an independent, highly precise measurement of the cosmos. As we approach the 2026 data release, this combination of structural and expansion data will confront a crisis that threatens modern physics. We now have the tools to measure both the early and late universe, but the results are tearing our models apart. Why are current measurements of the universe's expansion rate hopelessly at odds with one another? That persistent contradiction in modern astrophysics is known as the Hubble Tension. It represents a fundamental crisis in our ability to measure the Hubble constant, denoted as h0, which dictates the current absolute expansion rate of the universe. To understand this tension, we must look at how cosmologists calculate this expansion. They generally rely on two completely independent methods, one anchored in the ancient physics of the early universe, and another based on direct observation of our local, modern cosmic neighborhood. The early universe method depends on the cosmic microwave background, or CMB. By analyzing this relic radiation emitted just 380,000 years after the Big Bang, the Planck collaboration established a highly precise baseline measurement of the young cosmos. Using the standard cosmological model, known as lambda CDM, the Planck data predicts that the universe should currently be expanding at a rate of approximately 67.4 kilometers per second per megaparsec. This sets a rigid, model-dependent expectation for local galaxy recession. However, the late universe measurements tell a completely different, purely empirical story. Teams like the SHOES collaboration calculate the expansion rate by observing local phenomena, specifically Cepheid variable stars and Type 1a supernovae, creating a highly calibrated distance ladder. When astronomers directly measure the recession velocities of these local supernovae, they find an expansion rate of about 73.0 kilometers per second per megaparsec. This creates a glaring gap between the predicted early universe rate and the observed late universe reality. This discrepancy is not a minor rounding error. The mismatch has reached a statistical significance of roughly 5 sigma. In particle physics and cosmology, a 5 sigma discrepancy means there is less than a 1 in a million chance that this difference is merely a statistical fluke. It is crucial to dispel a common misconception here. The universe is not expanding at 2 different speeds simultaneously. Rather, this tension exists between our independent measurements and models, implying that our underlying framework of cosmic evolution might be fundamentally flawed. There are 2 primary ways the scientific community might resolve this crisis. The first suggests unrecognized systematic errors within the measurements themselves. For instance, the calibration of the local distance ladder could be artificially skewed by factors like stellar crowding around Cepheid variables. If new observations from advanced observatories force a recalibration of this distance ladder, the local measurements might shift downward to perfectly align with the CMB predictions. This would effectively dissolve the tension, confirming our existing cosmological models without requiring new laws of nature. Another proposed alternative is that our Milky Way galaxy resides in an unusually empty region of space, often called a local void. This localized underdensity could artificially inflate our nearby expansion measurements, creating an illusion of a faster global recession rate. But if these systematic errors and local anomalies are definitively ruled out, the alternative resolution is far more profound: new physics. It would imply our standard model is missing a fundamental mechanism governing how dark energy behaved over the last 10 billion years. To finally settle this escalating debate, cosmologists need a completely independent, unbiased arbiter. They require a geometric dataset massive and precise enough to map the expansion history continuously, bridging the vast epoch between the ancient CMB and modern supernovae. This glaring mismatch between the ancient and modern universe requires an unprecedented survey to track the evolution of the cosmos. How will Euclid's impending 2026 data release act as the ultimate tiebreaker for the Hubble Tension paradigm? To resolve the Hubble Tension paradigm, astrophysics requires an independent arbiter capable of bridging the cosmic timeline. That arbiter arrives in mid-2026 with the European Space Agency's Euclid Data Release 1, or DR1. This dataset is engineered to break the deadlock. It is critical to understand that DR1 is not the final data release of the mission. It is only the first statistically massive milestone of a 6-year survey, encompassing roughly 2,500 square degrees of high-precision survey data and initial deep field catalogs. The current cosmological crisis exists because we have conflicting data from 2 extremes. The Planck satellite measured the infant universe via the cosmic microwave background, while local observatories measure nearby supernovae. Between these 2 extremes lies a vast, poorly constrained intermediate epoch. DR1 will finally illuminate this intermediate gap. By surveying the sky across vast distances, the 2026 data will map the expansion history of the universe specifically at redshifts between 0.9 and 1.8. This covers the critical period when cosmic expansion began accelerating. To achieve this, DR1 relies on a combined analytical approach. For the first time, researchers will apply Baryon acoustic oscillations and weak gravitational lensing simultaneously across the exact same massive galaxy samples, eliminating the cross-calibration errors that plague mixed datasets. Operating across the 2,500 square degrees of the first year's data, this dual mechanism strategy directly serves the core mission requirements document to map the expansion history of the universe to an unprecedented precision of 1%. At 1% precision, DR1 will forcefully arbitrate the Hubble tension. If the new expansion rate precisely matches the early universe predictions, it will strongly imply that our local supernovae measurements contain hidden, unrecognized biases that artificially inflate the local Hubble constant. Conversely, if Euclid's intermediate data perfectly tracks backward from the faster local expansion rate, the tension flips. It would demonstrate that local measurements are accurate and that we have fundamentally misinterpreted the physics governing the cosmic microwave background. Yet, the most disruptive alternative explanation is that DR1 might confirm both previous measurements are entirely correct. Rather than settling on one value, the 2026 data could show a distinct transition in the expansion rate that neither current model predicts. If Euclid observes this shift, it would prove that the lambda CDM model, the prevailing standard model of cosmology, is fundamentally broken. It would necessitate an entirely new framework of physics to explain how the expansion rate changed between the early and late universe. This arbitration is not guaranteed, and the mission carries its own severe uncertainties. Because Euclid cannot take precise spectroscopic measurements for every single galaxy, it relies heavily on photometric redshift estimates to determine billions of cosmic distances based on color filters. Systematic errors in Euclid's own photometric redshift algorithms could introduce a new mission-specific bias. If these distance calculations are slightly skewed, the resulting data could falsely manipulate the apparent expansion history, further complicating the problem rather than resolving the existing tension. You would know this effort failed if the DR1 data yields a Hubble value that wildly fluctuates across different sky sectors, rather than definitively settling on or between the two established values. That would render the tiebreaker completely inconclusive. To successfully serve as this tiebreaker, the telescope must look back cleanly through the exact intermediate epochs where dark energy transitioned from a minor factor to dominating the cosmos. What does a 10 billion year timeline actually look like in the Euclid data? To understand what a 10 billion year timeline actually looks like in the Euclid data, we must treat the telescope as a time machine. Because light operates at a finite speed, peering deeply into the fornax, north, and south deep fields inherently means looking back into early cosmic history. Euclid accomplishes this mapping by capturing photons that have traveled for up to 10 billion years. This process translates a spatial three-dimensional map into a four-dimensional historical record, yielding distinct chronological slices of how the universe expanded and evolved. It is crucial to note that Euclid does not record a literal video of a single galaxy growing over time. Instead, it captures billions of static snapshots of different galaxies at varying ages, allowing astrophysicists to infer a general statistical evolutionary path. To organize these snapshots into a cohesive timeline, scientists rely on the combination of Euclid's VIS and NISP instruments to calculate photometric redshifts. As the expansion of space stretches the light emitted by ancient galaxies, their apparent color shifts dramatically into the infrared spectrum. By measuring this precise color shift across multiple wavelength filters, the photometric redshift technique allows astronomers to estimate the distance, and consequently the age, of galaxies located at redshifts greater than z=2. However, this methodology possesses an inherent epistemic boundary. Photometric redshift calculations, based purely on broadband color filters, are fundamentally less precise than measuring exact emission lines with a dedicated spectrograph, creating a statistical blur along the line of sight. This line of sight uncertainty means individual galaxy distances carry a measurable margin of error. Yet, because the deep field catalogs contain such an overwhelming volume of targets, the aggregate statistical average effectively reconstructs the dark matter architecture across vast cosmological epochs. The ultimate data output is a massive, multi-layered, three-dimensional map of cosmic history. Each redshift slice represents a distinct era of structure formation, showing exactly how dark matter halos clustered, merged, and grew under the competing influences of gravity and dark energy. There remains an alternative interpretation to consider when analyzing these structures. Some researchers suggest that apparent evolution in galaxy architectures could be driven primarily by local environmental factors and immediate galactic neighbors, rather than a universal timeline of dark matter clustering. To eliminate this alternative, Euclid's data must track the growth of massive cosmic webs across distinct eras. A discovery that distant, ancient massive galaxy clusters are statistically identical in structure to modern local clusters would fundamentally break our current models of dark matter assembly. Current cosmological paradigms predict a clear directional progression in the data. The deep fields should reveal a younger universe where early, chaotic webs of dark matter slowly condense into the highly structured, massive nodes that host today's localized superclusters. Capturing this 10 billion year transformation requires extreme sensitivity, achieved only by staring at the same 40 square degree patches of sky for extended durations. It pushes Euclid's optics to their absolute limits to uncover the faintest background objects ever surveyed by a wide-field space telescope. Yet, this profound journey into deep time generates a mathematically rich byproduct. While hunting for massive dark matter halos 10 billion light-years away, the deep fields are simultaneously capturing incredibly faint, low-mass objects much closer to our own galactic neighborhood. These localized discoveries represent an entirely different kind of astronomical treasure trove hidden within the dataset. What unexpected phenomena are hiding in the foreground of these deep cosmological exposures? To answer what hides in the foreground, we have to look at the concept of cosmic bycatch. Because Euclid stares so intensely into the deep universe, it inadvertently captures ultra-faint local phenomena drifting right in front of the lens. It is important to clarify that Euclid was never designed to be an exoplanet hunter. Its hardware was specifically calibrated to measure cosmological geometry, making any planetary discovery an entirely secondary benefit of its prolonged deep field exposures. The mechanism here relies on the exceptionally high signal-to-noise ratio achieved during these long observations. By leaving the VIS instrument's shutter open over the deep fields, the telescope captures scarce photons from objects with extremely low surface brightness. One significant byproduct of this sensitivity is the detection of ultra-faint dwarf galaxies. These are small, localized structures highly dominated by dark matter whose faint glow is usually completely washed out by the overwhelming light of larger neighboring galaxies. We already possess concrete evidence of this capability from the pre-DR1 early release observations. This preliminary ERO catalog successfully identified several faint dwarf galaxy structures, proving that Euclid's optical thresholds can detect objects previously considered practically invisible. But the detection limits of the VIS instrument stretch even further down the mass scale, crossing directly into the substellar regime. The telescope is actively registering isolated point sources of light that emit almost no thermal radiation. This introduces the hunt for orphan or rogue planets. These are free-floating, planetary mass objects that were violently ejected from their original host star systems and now drift alone through the freezing expanse of the interstellar medium. Planetary science forecasts suggest that the 2026 DR1 release will contain unprecedented catalogs of these rogue planet candidates. Because Euclid observes such a massive volume of space simultaneously, it acts like a giant net sweeping up these faint anomalies. This perfectly highlights the multidisciplinary value of the DR1 dataset. A mission engineered entirely to map billion light-year cosmological structures is simultaneously providing researchers with an invaluable trove of data for local stellar and planetary astrophysics. There is, however, a critical uncertainty limit when evaluating these faint candidates. A presumed rogue planet could easily be a highly variable background active galactic nucleus masquerading as a local, dim point source in the photometric data. Furthermore, distinguishing a true local rogue planet from a very distant background brown dwarf requires incredibly complex follow-up observations. Euclid's onboard instruments are highly advanced, but they cannot perform the precise chemical spectroscopy needed to make this final determination alone. To firmly classify these objects, scientists will rely on spectroscopic follow-up from the James Webb Space Telescope. If JWST reveals that all these presumed rogue candidates actually possess extreme cosmological redshifts, the local orphan planet hypothesis would be entirely disproved. Even with these classification challenges, the bycatch of the deep fields proves that DR1 is much more than a map of dark matter. It is a comprehensive census of the dark universe, logging everything from rogue planets to dwarf galaxies. Whether tracking local planetary orphans or massive billion light-year filaments, the ultimate goal of DR1 is to place the actual laws of gravity on trial. Could the anomalies hiding in this upcoming data indicate that Einstein's theory of gravity is fundamentally incomplete? If the anomalies hiding in this upcoming data prove real, they might force us to confront a profound question. Is Albert Einstein's theory of gravity fundamentally incomplete? For over a century, general relativity has stood as the undisputed bedrock of theoretical physics. It perfectly describes the orbit of Mercury, the bending of starlight around the sun, and the violent mergers of black holes. But there is a glaring, largely untested caveat to this phenomenal record of success. Every definitive triumph of general relativity has occurred on relatively small, local scales within star systems or isolated galaxies. Cosmologists have simply assumed these exact same gravitational laws apply identically across billions of light-years of empty cosmic space. The 2026 Data Release 1 will put that massive assumption to the ultimate test. Euclid is doing far more than just mapping where galaxies are located. It is meticulously measuring the precise rate at which cosmic structures clump together over time. Gravity is the primary engine of this cosmic clumping. By observing how rapidly dark matter halos merge and grow across a 10 billion year timeline, scientists can extract a crucial metric known to cosmologists as the growth of structure parameter. This specific parameter will be derived directly from the DR1 shear catalogs, massive datasets recording the microscopic weak lensing distortions of billions of background galaxies. It provides a direct, measurable history of gravity's pulling power across different cosmological epochs. Cosmologists will take this measured growth rate and compare it directly against the theoretical growth rate predicted by the standard lambda CDM model. That baseline model strictly relies on Einstein's unbroken general relativity operating universally. If Euclid's structural maps reveal that galaxies clustered together faster or slower than Einstein's mathematical framework allows, it would signal a profound breakdown of the standard model. It would strongly indicate that gravity requires modification on vast cosmological scales. A critical distinction must be made here regarding theoretical physics. Modified gravity theories do not seek to prove Einstein simply wrong about how apples fall or how planets orbit their local stars. Instead, they seek to expand his framework to encompass vast, intergalactic distances he never had the observational data to consider. This potential elevates Euclid from a tool measuring parameters within a model to an instrument capable of replacing the model itself. However, extracting a pure, undeniable signature of modified gravity is notoriously difficult. The universe is messy, and scientists must rigorously separate genuine gravitational anomalies from the chaotic astrophysical feedback generated by normal, baryonic matter. supermassive black hole winds, violent supernova explosions, and shifting gas dynamics can blow matter apart, artificially slowing down the growth of structures. Furthermore, even the tiny masses of elusive background neutrinos can smear out the cosmic web. An apparent anomaly in the growth of structure might just be complex gas dynamics masking standard gravity, rather than a breakdown of general relativity. Only Euclid's unprecedented statistical volume can untangle these turbulent baryonic effects from fundamental physics. But what if Euclid's data definitively shows that structure growth perfectly matches general relativity predictions at all epochs and scales? If Einstein's gravity holds true, the anomaly must lie in the other mysterious force stretching the universe apart. Is the energy pushing the cosmos toward its fate a rigid constant, or a dynamic, evolving field? To answer whether the energy pushing the cosmos toward its fate is a rigid constant or a dynamic field, cosmologists rely on a single critical metric. This mathematical parameter is known as the dark energy equation of state, represented by the letter W. In cosmological thermodynamics, the equation of state is defined by a surprisingly simple mathematical ratio. It is calculated by dividing the pressure exerted by the dark energy field by its overall thermodynamic energy density. For normal matter, like the gas in stars or clouds of cosmic dust, this ratio is positive because pressure and density scale together. But dark energy exhibits a bizarre property. It possesses negative pressure, which acts as the anti-gravitational engine driving accelerated cosmic expansion. Under the current standard model of cosmology, known as lambda CDM, the theoretical prediction for this parameter is highly specific. The baseline model asserts that W is exactly -1, meaning the ratio of pressure to density remains completely static over cosmic time. A common misconception is that a value of exactly -1 implies dark energy is merely a mathematical placeholder rather than a physical reality. In truth, a W of -1 simply means dark energy is a perfectly stable inherent property of the vacuum of space. The primary scientific objective of the upcoming 2026 Data Release 1 is to constrain the precise value of W to an unprecedented level of statistical accuracy. Euclid will accomplish this by strictly analyzing how the universal expansion rate has changed over the last 10 billion years. This extreme precision will be achieved through a highly rigorous analytical technique. Euclid's ground processing segment will mathematically combine the distance constraints derived from baryon acoustic oscillations with the deep field cross-correlation data extracted from weak gravitational lensing. By merging these two independent cosmological probes, researchers can measure the exact volume and geometric shape of the universe at different evolutionary epochs. If dark energy has evolved over time, the value of W extracted from this combined dataset will inevitably deviate from exactly -1. However, some theoretical physicists argue that applying an equation of state to dark energy might be fundamentally flawed. This alternative perspective suggests that dark energy is not a traditional fluid or a thermodynamic field that possesses a measurable pressure at all. Instead, these alternative models propose it could simply be a purely geometric property of spacetime boundaries, rendering the pressure-to-density ratio a theoretical illusion. Yet, until we have the immense DR1 dataset, W remains our most rigorous empirical tool to test these boundaries. Extracting this specific parameter from the cosmos is fraught with immense observational challenges. Instrumental noise within Euclid's visible and near-infrared detectors, combined with microscopic errors in calculating photometric redshifts for billions of distant galaxies, can severely distort the final thermodynamic calculations. If not perfectly calibrated out of the raw data, these systemic errors could easily create artificial statistical drifts in the calculated value of W. Such instrumental anomalies could mimic the elusive signatures of new, exotic physics, effectively misleading the entire scientific community. To definitively validate the baseline lambda CDM model, the vast DR1 dataset must prove that W is exactly minus 1.000, presenting zero statistical variance across all observed epochs. Any confirmed fraction above or below that rigid boundary line fundamentally shatters the current cosmological paradigm. Ultimately, the precise empirical value of this single mathematical number leads to two vastly different physical interpretations of what the dark universe actually is. Are we dealing with Einstein's unchanging cosmological constant or a shifting, dynamic quantum scalar field? The distinction between these two outcomes fundamentally alters our understanding of the vacuum of space. If Euclid's data release 1 confirms that W equals exactly -1 across all epochs, Einstein's original cosmological constant holds true. In this static scenario, dark energy is simply an intrinsic property of the space-time vacuum itself. As the universe expands, the density of this energy remains perfectly constant, smoothly driving the acceleration of the cosmos without ever diluting or changing form. But if Euclid's deep fields reveal that the equation of state deviates from -1, we enter the domain of dynamic scalar fields. This theoretical framework, often called quintessence, proposes that dark energy is not a rigid property of space, but an evolving quantum field. To be clear, a scalar field does not imply the universe possesses intent or consciousness. It is a strictly physical concept, representing a specific numerical value assigned to every point in space and time, much like a fluid's temperature distribution or atmospheric pressure. A varying W indicates that the energy density of the vacuum actually changes as the universe stretches. Quintessence models suggest this field can roll down potential energy gradients, meaning the repulsive force of dark energy could grow stronger, weaken, or even reverse course. The critical evidence will emerge from Euclid's time evolution analysis of W. By isolating specific redshift bins within the deep field data, scientists will track how the dark energy equation of state behaves across distinct eological scale eras, looking for any chronological drift. However, detecting a shift in W does not immediately guarantee the existence of quintessence. There is a documented risk that an evolving equation of state might merely be a phantom effect, an artifact of our foundational cosmological assumptions. Standard models assume the universe is perfectly homogeneous and isotropic on the largest scales. If we happen to be observing from within a massive, statistically underdense cosmic void, the local expansion rate could mimic the signature of a dynamic scalar field. To disprove this void illusion, Euclid's analysis must cross-reference data across the north, south, and fornax deep fields. If W appears to fluctuate wildly and inconsistently across different patches of the sky, the scalar field theory would face severe mathematical contradictions. Conversely, if DR1 proves a consistent, universal evolution of W across all fields, it will completely rewrite fundamental physics. It would mean the acceleration of the universe is driven by a distinct, previously undiscovered fundamental force operating alongside gravity, electromagnetism, and the nuclear forces. This discovery would shift the ultimate fate of the universe from a foregone conclusion to an open question. A dynamic field could eventually decay, halting cosmic expansion, or it could intensify indefinitely, leading to a scenario where space-time itself is torn apart. Euclid DR1 transforms W from an abstract mathematical metric into a tangible test of reality. We are no longer just measuring how fast galaxies recede. We are actively probing the structural identity of the vacuum that separates them. Extracting these profound physical truths from the sky is not just a telescope problem. The raw telemetry beamed down from the L2 Lagrange point is fast, messy, and riddled with instrumental artifacts that obscure the delicate cosmic signal. Translating these faint optical distortions into a definitive verdict on Einstein's legacy requires an unprecedented computational infrastructure. How exactly do scientists physically process the petabytes of ground data required to find these answers? To extract the dark energy equation of state from billions of distorted galaxies, the scientific battleground shifts from the vacuum of space to the Euclid science ground segment. This distributed supercomputing network is the hidden engine of the entire mission. Every single day, the spacecraft beams down approximately 100 gigabytes of raw, compressed telemetry from its orbit at the second Lagrange point. By the time data release 1 drops, the ground segment will have ingested and processed petabytes of information. There is a persistent misconception that space telescopes beam down ready to view images of the cosmos. In reality, Euclid transmits raw, deeply noisy numerical data, specifically the electrical charge counts accumulated at its Billion-Pixel VIS detector. Before any cosmological shape measurement can begin, this telemetry must undergo a grueling computational marathon. Algorithms must systematically identify and erase cosmic ray strikes that bombard the sensors in deep space, masquerading as high-energy starlight. The processing pipeline must also mathematically model and correct for radiation degradation within the silicon detectors themselves. As high-speed protons damage the sensors over time, charge drops alter the apparent shapes of galaxies, threatening the delicate, weak lensing measurements. Once the sensor artifacts are mapped and mitigated, the supercomputers tackle image alignment. Millions of individual exposures must be stitched together with sub-pixel precision, correcting for the spacecraft's microscopic thermal fluctuations and pointing jitters during its long stares. The computational burden multiplies when scientists extract photometric redshifts. To determine the distance to billions of galaxies, the ground segment must cross-reference Euclid's ultra-sharp visible light catalogs with its near-infrared spectrometry, building a three-dimensional map from two-dimensional data. No single facility on Earth can handle this astronomical throughput alone. The science ground segment operates across 9 international data centers, sharing the computational load through millions of synchronized CPU hours to transform electron counts into pristine galaxy catalogs. This intense reliance on software introduces a critical vulnerability to the mission. The data pipelines are so complex that subtle software artifacts or undetected algorithmic biases could accidentally manufacture the very cosmological signals scientists are desperately looking for. A systematic error in how the algorithm cleans the VIS telemetry could artificially distort galaxy shapes across the sky. If uncorrected, this manufactured weak lensing signal would result in fundamentally flawed constraints on dark matter and dark energy. To prevent this, the science ground segment routinely processes entirely simulated universes alongside the real telemetry. By feeding artificial galaxies with known dark matter parameters into the pipeline, scientists can calibrate their software and hunt for hidden processing biases. Some computer scientists argue that future missions might bypass these massive deterministic pipelines entirely. Emerging AI-driven neural networks could theoretically reconstruct clean galaxy shapes directly from raw telemetry, achieving the same precision with a fraction of the computational overhead. But for data release 1, classical supercomputing brute force remains the ultimate arbiter of truth. The petabyte-scale ground segment is the only barrier separating instrumental noise from a genuine revolution in our understanding of the dark universe. This grueling computational marathon is what separates public relations from rigorous astrophysics, which raises an immediate question. If the science requires years of supercomputing, why are the stunning early release images already published by Euclid insufficient to solve the dark universe? The stunning early release observations published shortly after Euclid's launch served a very specific purpose, but they cannot solve the dark universe. These initial images were essentially a proof of concept, designed by the European Space Agency for public outreach and critical instrument verification. While these early snapshots provided spectacular views of the Perseus cluster and the Horsehead Nebula, they represent only a tiny fraction of the sky. In the realm of precision cosmology, a few scattered, beautifully resolved galaxy clusters hold very little statistical weight. There's a common misconception that because we've already seen these breathtaking pictures, the primary scientific discoveries are complete. In reality, observational astronomy and statistical cosmology operate on entirely different scales of evidence and data volume. To understand the true nature of dark energy, scientists cannot rely on localized anomalies or isolated patches of deep space. They require an immense accumulation of independent galaxy shape and distance measurements to average out local cosmic variations. The fundamental mechanism of Euclid science relies on driving statistical error bars below a strict 1% threshold. Achieving this level of precision demands a sheer volume of data that the early release observations were never intended to provide. This is exactly where Data Release 1 fundamentally changes the paradigm of the mission. Scheduled for mid-2026, DR1 marks the definitive transition of Euclid from a machine producing pretty pictures to a rigorous precision laboratory. The evidence anchor for this transition is the massive leap in observational footprint. DR1 will expand the analyzed survey area from a handful of target regions to a contiguous 2,500 square degrees of the sky. This release will encompass the entirety of the telescope's first full year of survey operations, including the initial deep field results. It provides the first dataset large enough to map the expansion history of the universe with mathematical rigor. While the early release data alone is sufficient to rule out the most extreme, highly speculative alternative theories of gravity, it cannot pinpoint the exact equation of state. DR1 provides the baseline required to test general relativity at cosmological scales. If statistical analysis were to show that the variance in the first 100 square degrees perfectly matched the full 2,500, the larger survey would be mathematically redundant. However, the universe is inherently clumpy, necessitating this massive scale. Despite the unprecedented scale of the 2026 data drop, the scientific community acknowledges a significant boundary of uncertainty. Even the massive footprint of DR1 may still fall short of definitively resolving the entrenched Hubble tension. The discrepancy between early and late universe expansion rates is incredibly stubborn. Cosmologists anticipate that while DR1 will severely constrain the models, a definitive break in the tension might actually require waiting for the subsequent data release 2 or 3. Nevertheless, as the ground segment pipelines process petabytes of information toward the 2026 deadline, scientists are bracing for a foundational shift. DR1 will provide the robust constraints on dark energy that theories have lacked for decades. The release of this massive catalog is not just about refining the mathematics of cosmic expansion, it is about predicting the ultimate timeline of reality. In the next chapter, you will find out exactly what this upcoming milestone means for the final fate of the cosmos. What exactly does this upcoming milestone mean for the final fate of the cosmos? By mid-2026, the first official data release will transform billions of galaxy measurements into a geometric map capable of predicting how the universe ends. The ultimate deliverable of this massive mapping effort is calculating the exact value of W, the dark energy equation of state. This single thermodynamic number describes how the density of dark energy changes as space-time stretches over billions of years. If the 2026 data confirms that W equals exactly -1, we live in a universe governed by a standard cosmological constant. In this scenario, the cosmos faces a big freeze, expanding infinitely as galaxies drift into absolute isolation. However, if the Euclid data reveals that W is even slightly less than -1, the implications become far more violent. This points to a phantom energy model, where the repulsive force of dark energy accelerates exponentially over time. In a phantom energy universe, this acceleration eventually outpaces all fundamental physical forces. The expansion would forcefully tear apart galaxy clusters, then solar systems, planets, and finally the atomic fabric of matter itself in a catastrophic big rip. There is also an alternative cosmological explanation where dark energy is not a permanent fixture. In a cyclic universe model, this current phase of acceleration is temporary and will eventually reverse, pulling everything back into a dense, big crunch. Of course, predicting the ultimate end of time carries an inherent scientific limit. Humanity's attempt to extrapolate a 10 billion year observational timeline into the infinite future assumes that no novel physics will emerge in the distant cosmos. The only way to completely disprove these expansion metrics would be discovering a previously unknown fundamental law of physics. Such a discovery would have to require the universe to be temporally infinite and entirely static, overturning general relativity. We must also avoid a common misconception. Euclid will not hand us a finalized, absolute answer on a silver platter. Instead, Data Release 1 will provide the tightest mathematical constraints ever placed on these competing cosmological models. As the most detailed three-dimensional map of cosmic history ever assembled, this release represents the transition from theoretical debate to empirical measurement. We are finally applying high-precision geometry to existential questions that humanity has debated for millennia. Right now, the telescope sits orbiting the L2 Lagrange point, quietly downlinking petabytes of structural data back to Earth. The definitive answers regarding phantom energy, the Hubble tension, and our ultimate cosmic destiny are currently hidden within those raw bits. The global network of ground segment supercomputers is steadily crunching through the noise, mapping the shadows of dark matter clumps and measuring the microscopic stretching of background starlight. The raw material for a paradigm shift is already in human hands. When the embargo lifts in 2026, the scientific community will face the ultimate tiebreaker for the nature of reality. We will finally see if Einstein's framework holds firm across cosmic scales, or if the dark universe demands new physics. The countdown to Data Release 1 has officially begun, and the resulting geometric constraints will dictate the next decade of astrophysics. When the data finally drops in 2026, which side of the cosmological crisis will you be on? Let us know below.